Welcome back to the final video for Lagrange multipliers. Right. So here, let's do an example that's maybe a little less straightforward than most examples, or usual examples, I should say. So here we're asking to find the points on the conic section which are determined by this cone and this plane, which are closest to the origin. Right? So remember, a conic section is a circle, an ellipse, a parabola, or a hyperbola. Right? And they're all created by taking a plane and intersecting it with this double cone. Okay? So we actually don't really need to know which conic section that is. If you're curious, you can find out, but there's really no need for finding it out. What we do need to know is what is the function we are trying to extremize here, or minimize in this case? Well, we're looking for points which are closest to the origin, so that should mean we're trying to minimize the distance function. Right? So we're trying to minimize this distance from xyz to 0, 0, 0. Okay? And that's simply just x squared plus y squared plus z squared, all square rooted. Well, you can imagine we're going to have to take a gradient of this thing, and that's kind of messy. The nice thing about this particular thing is we can use f of xyz just as x squared plus y squared plus z squared instead. Now, why can we do that? Well, f is always positive and d is always positive, and also d has minimums exactly where f does. Or sorry, d has minima exactly where f does, which is very convenient, actually, right? So we don't have to deal with taking the derivative of that square root, because that gets kind of bad and messy. So how do we do this now? Right? What are our two constraints? Well, the constraints, well, the conic section is the curve of intersection of the cone and the plane. So the constraints, of course, are these two. So we can take our constraints to be g equals x squared plus y squared minus z squared equals 0, and h equals x plus y minus z plus 2 is 0. Right? And this is just that trick of taking everything to one side. All right, so we can now set up our Lagrange multiplier system. Right? Well, actually, well, yes, we can, but we need to take the gradients. So gradient of f is, of course, just 2x, 2y, 2z. Gradient of g, well, what is this? This is 2x, 2y, and minus 2z. Okay? And finally, gradient of h, well, that's just 1, 1, minus 1. Right? Nothing too bad there. All right. So now let's set up our Lagrange multipliers. Well, the Lagrange multiplier system. Right? So here we compare the x components. So we have 2x. Now remember, the first part is gradient of f equals lambda gradient g plus mu gradient h. So we're going to have lambda 2x plus mu times 1, so just mu. Right? The second equation, we compare the y components. So lambda 2y plus mu. And then 2z is, this time, there's a minus here. So minus, well, I guess this doesn't matter. Minus 2 lambda z minus mu. Right? I know I messed up. It's not very consistent, but it's okay. All right. So now we also have, x squared plus y squared minus z squared is 0, and x plus y minus z plus 2 is 0. Right? So now we have this system of 5 equations. Right? So let's number these again. 1, 2, 3, 4, and 5. All right. So now we have to go about solving this. Now this is where things can get a little bit tricky because there's so many equations. But thankfully, I chose an example that wasn't so bad here. So in equation 1, we can solve for mu to be 2x minus 2 lambda x. Right? In equation 2, and actually we can factor this. We can factor out the 2x and get 2x times 1 minus lambda. Here we can solve for mu just the same. 2y minus 2 lambda y, and of course that factors again. All right. So now what we've done is we've solved for mu in both of these cases. So these can combine together and give us 2x 1 minus lambda equals 2y 1 minus lambda. So what does this tell us? Well, let's call this equation 6. This says one of two things. Either x equals y, not x times y, but x equals y. So x equals y, or lambda is 1. That's the two ways in which this equation can be true. So the question is, which one do we start with? Well, which one should we start with? Let's confer with my notes here. It actually, I don't think matters. So let's start with lambda equals 1. I mean, it doesn't matter because we have to check both of them anyway. So let's start here with lambda equals 1. Okay? If lambda is 1, then, well, we can use this equation here, which is the same as equation 1, actually. So equation 1 becomes 2x equals 2x plus mu. Well, these cancel, and so mu is 0. So, okay. But then we can use equation 3. Okay? That tells us 2z is negative 2z. Remember, lambda is 1. Well, there's only one solution there. That means that z has to be 0. Okay. So we now have z is 0. Where do we go from there? Well, we plug that into equations 4 and 5. Okay. So we get equation 4 and equation 5 now are x squared. Well, actually, we don't even need equation 5. Because if we use equation 4, plugging in z equals 0 gives us x squared plus y squared equals 0. All right. Well, since x squared plus y squared equals 0, x squared is positive, y squared, well, I should say x squared is never negative, y squared is never negative. So if we add two non-negative things together and get 0, they must both be 0. So this actually tells us x is y is 0. Now, this is on the cone. In fact, it's sort of that pinch point on the cone, on the double cone, but it's not on this plane. So, but this contradicts 5. Okay, so thus lambda is not 1. All right, so what does that mean? If lambda isn't 1, then x has to equal y. That has to be what happens. Okay, so if x equals y, now what can we do? Well, we've already sort of used equations 1 and 2 to get that, so plugging it back in won't get us anything new. There's no x or y in equation 3, so we have to use equations 4 and 5. Okay, so equation 4, if we plug in x equals y, let's replace x with y, so we get y squared plus y squared minus z squared is 0, or in other words, 2y squared equals z squared. Okay, what about equation 5? Again, let's replace x with y. So y plus y minus z plus 2 equals 0. That's the same as saying let's do it the other way. Get these smears off the board here. This means that 2y plus 2 is z. So what do we do with that? Well, of course, we take this z and plug it into that z. Right? So these two together tell us that 2y squared is 2y plus 2 squared. Okay? So if we work out this side, this is 4y squared plus 8y plus 4. All right, so this gives us that 2y squared plus 4y plus 8y plus 4 is 0. So now we need to solve for y. Of course, that's just the quadratic formula. Right? So y is negative 8 plus or minus the square root of b squared, so 64, minus 4ac, so 4 times 2 is 8, times 4 is 32. And all of this is over 2a, so 4. Okay? So we have negative 8 plus or minus the square root of 32 over 4. Well, square root of 32 is 4 times 8. It's actually 16 times 2. So this is 4 root 2 over 4. In other words, we have negative 2 plus or minus root 2 for y. All right? So that's y. And now we just have to split that up into the two cases. So if we have y equals negative 2 plus or minus square root 2, if y is 2 plus root 2, and if y is negative 2 minus root 2. Right? What happens? What are the z and x values in this case? Well, this first case, so z is 2y plus 2. So z, which is 2y plus 2, is going to be negative 4 plus 2 root 2 plus 2. So it's 2 root 2 minus 2. And down here, same thing, z is still 2y plus 2, but this time we have negative 4 minus 2 root 2 plus 2. So this one is negative 2 root 2 minus 2. So those are the two z values, but then now we have to worry about what is x. Well, we can use equation 5 again, Except this time, actually, we don't need to go that far. I was just about to say things we do. We know x is y. So x equals y, and x equals y here. So we have 2 points. So we have minus 2 plus root 2, minus 2 plus root 2, and 2 root 2 minus 2. And likewise, minus 2 minus root 2, minus 2 minus root 2, and minus 2 root 2 minus 2. Okay? So here's the points, and here's the f values. So now we need to know what is the value of f at these 2 points. Well, plugging that in is going to take a little bit of work, so I'll use my handy little cheat sheet here. This is 24 minus 16 root 2 and 24 plus 16 root 2. Right? So remember, these two values are computed by taking these 2 points here and plugging them back into, where'd it go? F, x squared plus y squared plus z squared. All right, so which of these 2 is the closer point? Well, the closer point is given by this one. So this is the closest point. Right? So what is that other point? So if you graph these 2 equations and see what the curve of intersection is, you'll actually see it's a hyperbola. And so these 2 are sort of the vertex of each part of the hyperbola. And that means that this part happens to be the one that's closer to the origin. Okay? So hopefully that all made sense. I know Lagrange multipliers can get a little messy and intensive sometimes, but hopefully it all made sense, and you understood everything. I know I just repeated the same thing a couple times, but that's it for Lagrange multipliers. That's it for our section on derivatives, and see you in the next video for some multiple integrals.